Every single time we go to space, we blow up the rocket, not metaphorically. We literally ignite billions of dollars of precision engineering, use it once, and drop it into the sea. A single launch burns through roughly $5 million in propellant alone. The hardware gets discarded. The atmosphere gets punched through with enough force to rattle windows 50 miles away. We've been doing this since 1957, and for most of that time, nobody had a better idea. Until now. This is Japan's plan to build a structure so large it rewrites the economics of space, permanently. And the fact that you've probably never heard of it is the most interesting part of the story. There's a number buried in every rocket launch that almost nobody talks about. Getting 1 kilogram of cargo to orbit costs around $2,720, even with the cheapest rockets available right now. That's not the moon. Not Mars, just 400 kilometers above your head. Shipping a kilogram of cargo by air freight from New York to Tokyo costs about $5. Getting it to orbit costs 544 times more. The fundamental problem is physics. You need propellant to lift propellant. The more mass you want in orbit, the exponentially more fuel you need just to carry that fuel. Engineers call this the tyranny of the rocket equation. Konstantin Tsiolkovsky derived that equation in 1903. Despite a century of engineering progress, we haven't escaped it. We've just gotten better at living inside it. Reusability helps. Starship promises to push costs lower. But even the most optimistic projections for reusable rockets don't break through a certain floor. Because no matter what you do, you're still fighting gravity the hard way. Still exploding fuel to throw mass upward against a planet that wants it back. What if there was a way to climb to orbit instead? Not launched, climbed, steadily, mechanically, without fire. That's the idea behind the space elevator. It's older than NASA. Arthur C. Clarke wrote about it in 1979. Scientists have been drawing the diagrams for decades, but nobody could build it. Until a Japanese construction company called Obayashi Corporation announced in 2012 that they had a plan and a target date, 2050. That date is either the most exciting number in modern engineering or the most expensive fantasy ever committed to paper. The concept is almost deceptively simple. Attach a cable to Earth, stretch it up to geostationary orbit, 36,000 kilometers up. Then keep going, out to 96,000 kilometers, where a massive counterweight holds the whole system taut. At geostationary orbit, an object moves at exactly the same speed as Earth's rotation. It just hovers, forever, no fuel required. The cable doesn't stay up because it's lightweight. It stays taut because the counterweight at the far end is trying to fly away. Obayashi Corporation, one of Japan's largest construction firms, published a formal proposal with engineering specs, cost estimates, and a full construction timeline. The plan calls for a cable 96,000 kilometers long, anchored to an ocean platform near the equator. Robotic climbers ride the cable up to a station at GEO. Initial capacity of 30 passengers per trip, eventually scaling to regular cargo runs. The estimated cost sits somewhere between $7 and $10 trillion, roughly the GDP of Japan, and they think they can do it by 2050. The entire plan rests on one material, one substance that as of today we can produce in laboratory quantities but cannot manufacture at industrial scale. Without it, the cable snaps before it clears the atmosphere. Carbon nanotubes. A carbon nanotube is a sheet of carbon atoms rolled into a cylinder so small that 50,000 of them side by side are still thinner than a human hair. The tensile strength, the force required to snap it, is roughly 100 times that of the best steel alloys. A steel cable of the length required for a space elevator would snap under its own weight long before it reached orbit. Carbon nanotubes solve that. In theory. The problem is this: the longest single carbon nanotube ever produced in a laboratory is around half a meter. The cable needs to be 96,000 kilometers. That isn't a scaling challenge. That's a different category of problem entirely. In 2021, researchers at Cambridge published work showing that defect-free carbon nanotube fibers could be spun in short lengths. Progress, but nothing close to structural scale. Then something happened in 2023 that barely made the news. In 2023, a small experiment was sent to the ISS. The goal was to test how carbon nanotube fibers behave in the actual space environment, exposed to cosmic radiation, thermal cycling, and hard vacuum. The results haven't been fully published yet. Think about what that means. Material was sent to the most expensive laboratory in human history to test whether it could survive space, and the data is still being analyzed. What did they find? We don't know. But sit with this thought, because we're coming back to it. What if the material problem is closer to solved than anyone is letting on publicly? There are 3 major carbon nanotube research programs operating in the US, Japan, and China right now. All carry significant government funding. All are classified to varying degrees. SpaceX has filed patents on ultra-high tensile composite materials. Boeing's Advanced Materials Division has been notably quiet for years. We may not know the state of the material science because the people who know it don't have an incentive to tell us yet. The patents, the production lines, the breakthrough that makes this buildable could already exist. Or it doesn't, and the cable isn't ready. And in 2050 is wishful thinking. Either way, Obayashi is moving forward on the assumption that it will be ready. And their construction plan is more detailed than almost anyone realizes. Step 1 doesn't happen in space. It happens in the ocean. The anchor station needs to sit near the equator, in the middle of the ocean, away from commercial flight paths, storm systems, and seismic zones. The platform functions like a deep-sea oil rig scaled up by an order of magnitude. It needs to be mobile, capable of maneuvering the cable anchor point by small degrees to dodge debris in orbit. It needs its own power generation, a full port for supply ships, and launch infrastructure for the cable deployment system. Building this platform alone is a multi-decade project, but the engineering is understood. We build offshore platforms. We build large marine structures. Once the platform is operational, the clock starts on the hardest phase of the entire project, getting the first cable into space. Because the seed cable, the very first thread of this structure, has to get to orbit somehow. And the method Obayashi is proposing is stranger than you'd expect. The irony built into this entire project is this: to build the structure that replaces rockets, you need rockets. The plan calls for launching an initial 20-ton cable bundle into geostationary orbit aboard conventional rockets, multiple launches, multiple segments, assembled in orbit by robotic systems. This initial cable weighs 20 tons, not enough to carry passengers, not enough for heavy cargo, but enough to begin the process of self-reinforcement. Once the seed cable is deployed, stretched from the orbital station all the way down to the ocean platform below, the first climbers go up. Not passengers, machines. Reinforcement climbers, carrying additional cable material, wrapping it around the seed, building it thicker and stronger with every trip. Each climber run adds structural capacity, which allows the next climber to carry more mass, which adds more structural capacity. A self-reinforcing feedback loop, running continuously for the better part of 15 years. 510 reinforcement climbers. That's the number Obayashi published. 510 separate robotic ascents, each one thickening the structure until it can hold the weight of a full passenger car. And here's what nobody talks about. Nobody knows what breaks down first. A climber? The cable itself? The platform? The system has no redundancy during the build phase. If something fails in year 8, you're not starting over. You're diagnosing an engineering failure 50,000 kilometers above the Pacific, with no way to physically reach it. Obayashi's published timeline divides construction into 3 distinct phases. Phase 1 runs roughly from 2030 to 2035, covering platform construction and seed cable launches. Phase 2 runs 2035 to 2045 for the continuous climber reinforcement cycle. Phase 3 runs 2045 to 2050 for geostation construction and first passenger tests. The 2050 deadline is not arbitrary. It's tied to when Obayashi believes carbon nanotube manufacturing at scale will be viable. They're not waiting on the physics, they're betting on the chemistry. Peter Swan, president of the International Space Elevator Consortium, has publicly stated the timeline is achievable with sustained investment. Bradley Edwards, who wrote the technical reference work on space elevator design, is more cautious. He said publicly that material science is the wild card, and that everything else is just engineering. Japan's government has formally listed the space elevator as a priority research initiative. Funding is flowing. Academic publications are accelerating. But there's something about the 2050 date that almost nobody is saying out loud, and it's the thing that changes how you should think about this entire project. At geostationary orbit, 36,000 kilometers up, the design calls for a permanent station. Not a waypoint or a transit hub, a city in orbit. And this is the thing nobody is saying out loud about 2050. By the time this station is operational, it won't just be a destination. It will be a jurisdiction, a place with its own economy, its own supply chains, its own rules about who gets access. The initial design is functional, with docking ports for climber cars, fuel depots for deep space missions, and research laboratories. But the long-term renders show residential sections, hotels, observation decks with a view that no one alive has ever had. From 36,000 kilometers, you can see the entire sunlit face of Earth at once. Every continent, every ocean. The atmosphere is a tissue-thin blue line at the edge. Space is everywhere else. From GEO, getting to the Moon or Mars costs almost nothing in fuel compared to launching from the ground. You've already climbed out of the deepest part of Earth's gravity well. Deep space becomes routine, but none of this holds together without the counterweight. At the far end of the 96,000-kilometer cable sits the counterweight, 48,000 tons of ballast, stationed well beyond geostationary orbit. Without it, the cable goes slack. With it, centrifugal force keeps the entire system in tension from the ocean platform all the way to the outer edge. The counterweight doesn't have to be built from scratch. It could be a captured asteroid, mined and positioned at the right orbital distance. The materials needed to construct it might come from near-Earth asteroid resources, reducing how much mass needs to be launched from Earth at all. Which means the people who build this thing won't just be running a transit system, they'll be running the first off-world economy in human history, and the first passengers will be at the center of it. The first passenger runs are planned for around 2050, initial capacity of 30 people per car. The trip from the ocean platform to GEO takes approximately 7 days at climbing speed. 7 days, not 8 minutes like a rocket launch. No G-forces, no vibration, no launch window to hit. Think about what that changes. Space tourism has been defined by who can physically survive a launch. At 4 or 5 Gs, it's a young person's game. On a space elevator, it isn't. You could be 70, fragile, recovering from surgery, and still watch the planet shrink beneath you over the course of a week. Right now, getting 1 kilogram to orbit costs $2,720. With a space elevator at full operational capacity, that number drops to $10. That's not a 10% improvement, not 50%, not even close. It's a 99.6% reduction in the cost of reaching orbit. At $10 a kilogram, you can send a satellite to orbit for the price of a decent smartphone. You can ship manufacturing equipment to a lunar base for less than it costs to truck it across a continent. You can build a Mars mission out of affordable, replaceable components without betting a national budget on a single launch. Space stops being the domain of governments and billionaires. It becomes infrastructure. The same way the internet or the shipping container became infrastructure. The moment orbit is cheap, the 21st century becomes something unrecognizable from where we're standing right now. Energy from space becomes viable. Asteroid mining becomes profitable. Permanent off-world settlement becomes not just possible but economically rational. And all of it traces back to a cable, 96,000 kilometers long, anchored to a platform in the middle of the Pacific. One thread, holding the weight of everything that comes next. Tsiolkovsky dreamed of a tower reaching to the heavens in 1895. Clark turned it into fiction in 1979. Obayashi turned it into an engineering proposal in 2012, with a price tag and a deadline. Whether that deadline holds, whether the nanotubes arrive on schedule, whether the funding and the political will survive across 3 decades of changing governments and priorities, nobody actually knows. So I want yours. Drop it in the comments. Does this get built by 2050? Yes or no? And if you want to understand what $10 dollars does to the global energy supply, that video is on screen right now.